Hi, I'm Yan Zuo, and I'll talk about compiled models built-in exploits, uncovering pervasive bitflip attack surfaces in DNN executables. This is a joint work with Liu Zhibo, Yuan Yuan, Hu Sihang, Li Tianxiang, and Wang Shuai. Well, I know our paper has a long title, so let me first give you a quick distilled version of the talk so you know what to expect. So there are this new kind of DNN executables, and you can understand them as the compiled version of DNN models. And in this paper, we're going to review an attack on these DNN executables. So as an attacker, our objective is to deplete the intelligence of the model, for example, to make it see a ninja when looking at this photo of a panda. And in this talk, we are going to review an attack based on bit flips, for example, done using Rowhammer. And we'll reveal that there's pervasive attack surfaces in these DNN executables. In our attack, we'll assume a gray box, more restricted attacker than previous existing work. And using our method, the attacker can achieve 70% confidence in identifying the bits to flip. And only around 1.4 blips are required to deplete the complete intelligence of the model. Great, now we'll get into our preliminaries. So first, DNN executables. There are a type of executables compiled from DNN models by so-called deep learning compilers, like TVM from Apache and Glow from Meta or Facebook. And people want them mainly because of their performance. DNN executables are optimized at the computational graph level, so the model becomes more efficient. And they're also optimized for the target hardware platform that they'll be running on. So the maximum potential of the platform could be extracted. And what are bitflip attacks, or BFAs? This is a kind of attack that flips bits, data bits in the memory or DRAM. And the most prominent instance of it is Rowhammer, which is a hardware vulnerability triggered using only software. Basically, when you access the memory with some specific pattern and you do it so fast, you will trigger current leakage between those DRAM cells. And the data bits stored in those cells could get flipped. And currently, researchers have demonstrated this on basically every generation of memory modules that we have. So now you may be wondering, okay, does this works on DNN models? And the answer is absolutely yes. Researchers have found that they can manipulate the model's behavior by flipping bits in the model weights. And typically, this is a white box attack because you need to know the model weights in order to calculate the gradients, in order to decide which bits to flip. So for full precision models, like they're using a floating point number as weights, they only need a few flips to be attacked. On the other hand, for quantized models with integer weights, they will require a few more times flips to get the same attack performance. But as you'll see later, we'll show that this is not the case anymore. Yeah. And we'll now move on to our threat model and motivation. First, attacker objectives. As mentioned earlier, we want to achieve intelligence depletion. So for example, we want to turn classification models, which are the most frequent target, into random guessers. Like their accuracy should become something like 1 over the total number of classes after the attack. And here's the attack flow, basically for all these BFA attacks. So first, the attacker will have some locally generated model or executable in our case that they constructed using like whatever knowledge permitted by the threat model. And they will use their knowledge to figure out which bits to flip. And once they have decided on that, they will launch the real attack on the victim model in the remote environment. So recall that previous works have white box attackers who have access to like model weights and everything. And in our case, we mentioned before that we want a more restricted attacker. So our attacker does not have access to weights, which is actually more reasonable because weights are often confidential. This also means that there's no gradient-based search method available for us. And we only know the model structure as well as how to compile it to get the victim executable. So the question now becomes how to identify those vulnerable bits to flip given this constraint. And emphasis on identifying. We're not going to propose a new like Rowhammer technique here. Well, there's ample of them. And instead we are trying to figure out which bits to flip, how to identify them, so that you can like plug in your favorite Rowhammer technique and do the attack. And what will be the answer to that how question? Well, the answer is actually in the name, DNN executables. Remember that DNN executables are compiled code, which are the compiled version of those DNN operators used by the original model. So that means if we can flip the bits in the code, we can probably change the model's behavior. So we went on to establish a baseline. So in this baseline, the attacker, since the attacker already knows the offset of the victim executable's text session, which is where the code lives, they can decide which bits to flip by simply like randomly choosing some of them that are in range. And it turned out that it was pretty bad. The attack success rate, or ASR, was around 2%. But that means if we are to choose a random bit to flip in the victim model, then we would only succeed, we would only successfully downgrade it to a random guesser around 2% of the time. And sadly, in the other 98% of the time, they just lead to crashes or simply have no effects at all. So to gain more insights, we completed the random attack experiment with a more comprehensive survey. What we found was that pervasive attack surfaces do exist in like different models or data sets or compilers. But still, how to identify those vulnerable bits? They change with so many things. For example, they change with the model weights, the training data, but our attacker does not have access to any of those information because of our restricted threat model. So, but maybe we can look at things from another angle. Do vulnerable bits overlap? That is, if I have two executables compiled from the same model, but trained on different training sets, will they share their vulnerable bits? So we did some experiments, and the answer is yes. We found that two DNN executables compiled from the same model structure, but trained on different sets, they have around 45% of the vulnerable bits shared. So this means that there are transferable vulnerable bits, which means that a portion of the vulnerable bits work on more than one executables despite the different training sets. So the next step is to build an attack out of this discovery. To do that, we want to use more local executables during the local profiling phase and find the intersection of their vulnerable bits, which we'll call superbits for convenience. And how to build more local executables, like what data sets do we train them on? Well, it's an answer you may not expect. Just use random noise initialized with different seeds. We use these kind of data sets because we are inspired by studies in the machine learning community where they found that random data sets will regulate the model weights to gradually resemble weights in those well-trained models when they're used in phases like pre-training. And another advantage is that they minimize the biases. For example, if the victim trained their model on some like cat photos, and we train ours using X-ray images, then the data distributions would be a bit too far away from each other. So using random data sets is more of an unbiased choice in this sense. So we went ahead and generated many executables trained on different random data sets, which we call fake data sets for convenience. And we succeeded. If we use 10 fake data sets to find those super bits, we reach an ASR of around 70%. So we're now 70% confident that the flips we find will work on the victim executable. This is definitely much better than what we began with, like 2%. So we feel pretty satisfied with this result, so we continued on to our real-world experiments. So we set up our experiments on Blacksmith, a state-of-the-art Rowhammer toolkit for DDR4 memory. We tried the super bits we found on a wide range of victim executables. So, and they work really well in all cases. So here the accuracy change says that all models are now random guessers. So they're equipped with the eyes to see ninjas out of panda photos. And there's also no crash during the exploit. But the most important metric here, of course, is the number of flips, which is on average 1.4 flips to completely deplete the intelligence of the victim model. And in case you're wondering what that means exactly, take a comparison with DeepHammer, a state-of-the-art attack targeting model weights. So on average, they'll need about 12 flips to achieve the same attack performance, and we only need 1.4 on average. And they also need white box knowledge of the victim model to calculate gradients and decide which bits to flip, but we only have a gray box attacker, and we are much more restricted. So yes, in this talk, we've talked about the unique bit flip attack surfaces in DNN executables. We showed that attackers can be highly confident in identifying vulnerable bits in them and be highly effective when launching real attacks. And in the future, we'd like to call for more security research on DNN executables. Thank you.
Okay, thank you so much. We have time for questions. Any questions? Maybe I'll start with one. So your attack was kind of untargeted, right? So your goal is to reduce the accuracy to random guess or something. I was wondering if it's possible to also do it in a more targeted way. So let's say you don't want to go down to 10%, but you want to go to 60% because you don't want to be detected. Or let's say just target it for a class of kind of inputs. So you only want to misclassify pandas, but not anything else. So I was wondering if it's possible to do the flipping in a way that is kind of more targeted.
Yeah, so great questions, thank you. And so the first question is about how can we control the aggressiveness? And the answer is yes. And actually, I will talk about that in the next talk, which is about the defense. And actually, there are like different degrees of aggressiveness that these vulnerable bits have. So to maximize the effects, we are here just presenting the most aggressive ones, but there are definitely, you can definitely do that. Yes, so the second question is about how can we do targeted attacks in terms of like different classes. And well, yes and no. So there are more than one type of targeted attacks in the literature. So basically what we found, but we didn't present here due to time, is that we find that like most of these bit flips, they actually like kind of pin the victim model towards a specific kind of a specific class. So they do the pinning, which means that you can do to some degree you can achieve an end-to-one targeted attack. But if you want like one-to-one targeted attack, that we think would be more suitable with like weight-based the traditional methods. Yeah.
Okay, very good. Thanks so much. So I think we're out of time, so let's move on to the second presentation. Let's thank Injo again.